Hey, this is Professor Snell, E231. I had a question about I said in class, well, actually, I think in some classes I didn't even bring up the 0.2% offset yield strength or stress. And in others, I said, if you watch the video at the end, there's a link, by the way, to a video that shows you step by step how to do most things in the assignment um, to some level. But the way that I did the 0.2% offset yield stress in there is not the way we're doing it now. So this little video is clarifying how to do that. Um, okay, so first of all, the point of the 0.2% offset yield stress is that it's hard to tell where on this graph we go from the proportional or linear portion of the graph to the curved portion, basically. So I'm saying visually, it might, we could think it'd be up here, it might be here, I don't know, maybe it's down here. Um, so we need another method of figuring out where that is. And so this is how this is one way it's done. You hopefully remember, if not, let's just go over it, that that the slope of of whatever the linear portion of this data set is so stress over strain, right? That would be the slope, rise over run of this line. That is called Young's modulus or the modulus of elasticity. And we measure it in a very specific range. And the range is defined in terms of the strain values. And if you look in the assignment or look it up other places, well, maybe not other places because we're using an ASTM standard that defines this. It may be specific to these materials. It means it may be different in Europe, whatever. We're saying that we're going to define the Young's modulus between about 0.2% strain and, sorry, 0.05 and 0.2% strain. So it's going to be really a tight little range right in here. And the reason we're doing that is because as we start stretching this material, or we start adding loading it in tension, it's experiencing a stress, which is the load divided by the cross-sectional area. That it's gonna displace so in other words, this x, as soon as we start moving in the x direction, we're making the sample longer. That means its cross-sectional area is getting smaller. And so very quickly here, when we're up to here, this area is definitely smaller because we've gained some length, which is denoted by the strain, and therefore that line is not really straight anymore. So how do we just deal with this in the real world? So what you've done so far, hopefully, or what you're learning to do is we're taking the data so the position data is our delta L force data in newtons, and we're converting it first to inches and pounds, and then so that's we have our so in this case meters, right, times our meters to inches, which is this constant down here. We get a value, right? And we do the same thing with our load, so newtons, changing it to pounds. Then we apply our strain formula, which is going to be inches, right, divided by the original length or working length or gauge length that's here. That's been converted also. And then we divide our force in LBF by the area that we've calculated down here. And so what portion of these two, of the stress over strain, are we going to use to get our 0.2% yield strength? We said it was between 0.05 and 0.25% strain. So 0.05% is 0.0005. So essentially starting here, and I've colored, I use colors a lot in Excel. I've come down and said, okay, where is my 0.0005 percent? Oh no, I meant 0.0005 strain, which would be change in length over original length. So here it is, and I'm going to 0.25% strain, which is 0.0025, right? So these are the strain values that I'm going to use, and these are the stress values that are that correspond to them, right? To get the slope, so to get my actual accurate modulus elasticity, I can actually just calculate that. I don't need to come up here and do the 0.2% yield stress. And that I would do that by finding the slope of these points. And so if I come over here, I said, skip the ceiling math for a second. There's a formula, so equals slope, and I went by this range. So K 26 to 34 is my stress, and J 26 to 34 is my strain in this range here. So slope, that gave me a value. Then the ceiling math, which you don't have to do, but why would I have this, very exacting number on something that's not going to be that exact? So I use this function ceiling math, which basically is saying I'm going to round to the nearest, and then I tell it what that number is. So I said I want to round to the nearest 100,000. So that's what I've done here. So that's my actual experimental E value to be compared to my theoretical E value, which is here, right, that we looked up. But okay, how do we get this line here? And actually, the video shows you how to get the line, how to hide it, and apply the trend line. But so what we're saying is that then this is our stress over strain range that we're using to calculate our modulus of elasticity. So then we want to shift this over 0.2% along the x-axis and then extend a trend line up from that, or extend a trend line for that data set through our main data curve, and at the point where they intersect is our 0.2% offset yield strength. So how do I do that? Well, I just add 0.002 to, and I've done this a little bit more complexly here, but you can see my offset yield is 0.002, which would be 0.2%. I'm just adding that number to these values, right? So that's what that is. And so I've added those, and then I plot my 0.2% yield stress is, my x values are these where I added the 0.002, and my y values are the strain values for, it's the same strain values. So I'm sorry, the same stress values on the y-axis. So those two plotted together create, I'm actually going to, I'm just going to delete this for now. Select and move that away. So there's that data set that I then apply a trend line to, that what I'm doing is making it invisible by making it have no line, and then I'm adding a trend line to it. In this case, it's linear. Oops. I'd have to go back now and identify, let me see, give it some, I'll just give it a solid color at this point. Oh, right. See, there it is. It's that little dotted line there, and then I have to go back. This is look in the video. Then I have to play with the forward and backward periods to get it to go up through the data set. So look at the video for all of that. A couple other things I was maybe going to show you after looking at this. Oh, just in case you saw this in the video, I don't know if I did this in that video. This yield offset difference, these columns are just here to actually calculate the offset yield, this actual point. And so you don't need to do that for this assignment. It's just the point being, as I'm showing with ceiling math here, there's a lot of coding you can learn about Excel, and I encourage you to get more deeply into it. But for this assignment, all you need to do is have something that looks just like this. The only thing that's, I think, not in the video that you need is what I just showed you, which is how to do the 0.2% offset yield, which is based on the modulus of elasticity, which is calculated on a um, on strain values between 0.05 and 0.25% strain. All right, that's it. Hope that helps.